I do stuff with networks, and the talk that I'm going to do is pretty general about networks and network visualization. Green button to go forward, maybe. I have a degree in computer science. Yes. Thanks, Ben. So this is where the slides for the presentation are going to live. If you want to download them, this is the URL for that. So networks are a really cool thing. And people, when you tell them that you're talking about networks, first thing they think is Facebook, Twitter, social networks online. But they're pretty often very much broader than that. So anything that you can think of as a relationship can be represented in a network format, right? Networks between human beings, networks between machines, online networks, and so on and so forth. In R, there are a number of ways to actually deal with networks, with those graphs. And depending on where you come from, you might have bumped into some or other of them, right? So there are three big frameworks that you might end up using to kind of analyze network data and visualize it. One that I actually am going to talk about most today is the iGraph framework. So iGraph is a package that exists in R, in Python, and in C, C++. And so a lot of people use it, and it is really great for basic analysis and visualization of networks in R, right? All of the kind of basic stuff that you want to do in networks exists there. It's scalable, it's really easy to use, it's good. The second kind of set of packages that is actually used by a smaller number of people and more on the statistics side is the StatNet family of packages, right? So StatNet is a whole group of packages that do a bunch of different stuff with networks, starting from the basics, basic analysis and visualization, but also moving on to modeling, like trying to guess how networks are produced, right? What are the mechanisms that actually are behind the generation of a network, right? Does this network happen because, if it's a social network, because people, connect to others who are similar to them? Does the network evolve because we like to introduce others to friends of friends? Does it evolve because we like to reciprocate relationships? Stuff like that. We can model networks and kind of try to guess what are the generative processes behind those networks, right? This and a bunch of other kind of modeling problems are solved by the StatNet family of packages. And the last one, which is go back. The one that is also really cool is the RCNA package. RCNA is a package that tries to model network evolution and the way networks, the structure of the networks coevolves with the properties of the nodes in the network. So meaning, if you want to investigate how data changes over time, you have a social network, for example, you want to see how it evolves, you want to predict what will happen and how the characteristics of the nodes, the people, the machines in that network will change based on previous data, then RCNA is your package. And so what I thought I'd do today is just touch on a little bit of the basics, because I know that some of you have done a lot with networks and some of you have done probably not much work with them, and then do a few examples of more fun, advanced things. Okay, so what kind of stuff do we do with networks to begin with, right? The basic kind of ideas that I mentioned you can do perfectly with iGraph include things like find out what's important in the network. What are the key elements? Who are the important people? What are the important connections? What are the communities in the network, right? How does the network split apart into groups? If I have your social network, what are the kind of the groups that exist in it? Right? If I have a group of people that you're surrounded by, can I identify the central ones so that I can, inoculate them? Public health people do that a lot, because it turns out that if you're really popular, good for you, but for you is that you're most likely to get the flu, right? So popular people get sick first. If you get the flu, consider it a compliment. So one thing that that we do with networks a lot is try to identify how something spreads across this network, be it contagion of a disease or a meme of a rat on a skateboard or whatever it was, eating pizza or I forget. And so this is the example I like to give to students when I teach network classes. This is actually a node snapshot of my Facebook network. And the really cool thing about it is that knowing nothing about who I am or what my life is like, this kind of tells you a lot about, you can use just the structure of the network to guess a lot about what's happening, right? So each cluster in this kind of network represents a different context of life, right? Your friends from school, your friends from the office, your I don't know, bowling friends or whatever else you have. Geographic locations, right? I have 2 big clusters because I've lived on 2 separate continents. One fun thing that I do with the students is, whoops, if you really try, you can use network structure to identify someone's significant other. John Kleinberg had a couple of studies like this where he was using only the structure of the network, no additional information to guess who your significant other is. Turns out it's the person who's not the most connected one in your network, but it's the person who's connected to the most clusters. Right? They're the person who not only know a lot of the people you know, but actually know your family and your school and your work colleagues and everyone in every cluster. Not everyone, but like people from every cluster. And I think they even did a follow-up study that was a little creepy where you can pretty much guess with some certainty if people are going to break up based on the network structure, right? So if someone is not introducing you to all of those clusters and you've been together for a while, that is a reason for concern, right? So network analysis gets a little creepy like that, but the point is that we can learn a lot about people, machines, the internet from just structure, even if we know nothing about people's properties. So network data, what does it look like? A lot of you probably know this. There's many formats that it lives in, but this is kind of the most straightforward one that you'll probably bump into, which is just take a network and then describe all of the connections in it one by one, okay? And so this saves you some space. If you use a matrix or a different format, you may lose some space. You may have to do that eventually, but a lot of networks begin from this edge list format. So how do we do any of this stuff in iGraph? Well, this is a kind of a simple example. This is a very popular graph that all of the network scientists in the world love dearly. It's something that comes from data collected in the 70s. It's called the Zachary Karate Club, right? So this is actually a karate club at a university, and as the person who was collecting data about it was finishing up their work, they actually got into a huge fight and split apart. Right? So the club split into 2 separate clubs. And so ever since then, everyone who has any kind of algorithm that kind of predicts communities in networks or anything like that, first thing they do, they run it on this tiny little network of the karate club to see if it will appropriately predict the breakup of the network. So what we're doing here in the next few lines of code that are on the screen is just kind of opening the, loading the iGraph package, loading this Zachary Karate Club network, which is built in, and then doing all of the simple things that we mentioned, right? The degrees of the nodes, which is basically how many connections each node has, can be calculated. Other measures of centrality, for example, betweenness, which sounds like a weird word, but actually means are you kind of connecting groups of people in this network that would be otherwise unconnected, right? If you have high betweenness, that means a lot of information or connections have to go through you. You live on the lot of the shortest paths between other people in the network, so you can calculate that for both nodes and edges. Right, edge between a similar concept, similar idea, which edges in this network are really, really important. If you cut them, then you're disconnecting parts of the network, right? This kind of metrics are something that, for example, the Army is really interested in, looking at communication networks, network disruptions, and so on and so forth. Another way of calculating who's important in the network is so-called closeness metric, and it just tells you who the people are who are kind of at a shorter distance from everyone else in the network. So if you're distributing messages or things like that, then you want to look at that metric, right? And then the last thing that we're doing here on this slide is kind of doing a very simple plot of the network. And in iGraph, this is fairly straightforward. You just type plot, right? And you add the name of the network and a bunch of parameters that are kind of self-explanatory, that are named in pretty understandable ways. If I'm not mistaken entirely, there might be a list of parameters I am. Somewhere along the lines, there's a list of parameters and what each one is, but as you see, edge color, edge width, edge, whether the edge is curved or not, vertex color, frame color, those are all exactly what they sound like, right? So you can use those to kind of visualize the network in a simple way. So the next example is identifying communities in the network, right? So iGraph gives you a bunch of different ways to identify communities. The one that we are using here uses this edge betweenness idea. So basically it says, what are the important edges in the network that really connect otherwise kind of pretty disconnected groups? And what happens if we remove them? If we keep removing those long enough, we'll probably end up with separate communities in the network, right? And so this cluster edge betweenness function in iGraph can identify those communities for us, and then the rest of the code here is simply using the different communities to kind of change the color of the nodes on the network in this plot, right? So I'm just feeding the vertex color parameter in the plotting function, a vector of the colors based on communities. And here are, this is the long and boring list of parameters that you can also find in the help file that do exactly what they sound like they would do. But again, you should be able to download the slides if you ever want to read all of this. I'm not going to, do that to you now. A few other kind of things that we want to do with networks. Occasionally, we want to kind of track some characteristics that might be driving the formation of connections in the network. So for example, in human networks, one thing that often happens is reciprocity. You follow someone on Twitter, the probability of them following you back jumps up a lot, right? So reciprocity is this kind of idea that connections become symmetric. I follow you, you follow me. In some systems, the connections are inherently symmetric, but not in all of them. Transitivity is this kind of friends of friends idea, right? You're much, much more likely to be connected to someone if they already share some connections with you, right? If you have shared friends, in the human kind of social network example. Homophily is the idea that we see more connections in the social world between people who are similar, right? So I do a lot of political science stuff, and then there we try to see whether the left and the right have separate networks, and as it turns out, they're increasingly ever more separate, right? Highly separated, polarized networks where blue dots connect to blue dots and red dots connect to red dots, right? And proximity is another one. If you're studying any kind of digital network, then more often than not, the connections are proximate in space, right? So those are some other characteristics that we can and want to track occasionally with networks. And so, for example, here, we're taking our Zachary Karate Club network. It's because it's symmetric. Initially, we're going to turn it into a directed network, and the function for that is just as directed in iGraph. And we're saying just give the edges in this network an arbitrary direction, right? So now that we have directed edges, we can do stuff like checking for reciprocity, right? The idea that what % of the edges in our network are reciprocated that go between A and B and back from B to A. We can check for transitivity, right? Do we tend to see a lot of those triangles in the network where people are connected to friends of their friends and stuff like that. One thing that's really fun to explore, and it requires a little bit more complicated modeling, is tracing the evolution of networks over time, right? So basically, examining how the network evolves, and also checking whether we can predict what the parameters are that, if we tweak them enough, we can get to understand the evolution and see where it goes next, right? How networks develop. Doing the prediction model, it takes a little bit more time than we've got here, but one thing that is actually fairly straightforward to do is the visualization of dynamic network, and that's fun, right? So one way to do this is, as Michael was talking about, to use animations. And you can, as with any other kind of plot in R, you can animate network plots by just taking a bunch of network plots and then combining them in a sequence, right? But thankfully, there are more fun ways to do that with networks, because there are quite a few packages that take networks from R and then export them to JavaScript. Right, so you take your good old kind of boring network, and then you feed it to one of those packages, and it spits out a very pretty interactive network chart. Okay, so again, if we're doing dynamic networks, then we have to have a little bit of a different data format. Right, so now we not only need to know the connections, but we need to kind of have some idea of their sequencing time. Right? So the connection from John to Jill in this tiny little network is happening between 98 and 2000. And then the next one is 2002 to 2003, right? And then this one is 2004 to 2007. And then the last one, or the last two in this case, are happening, later in time. So you have a little bit of additional information in your data frame that tells you not only who is connected to whom, but also when that happens. And you can have similar information for the nodes in the network, right? When they show up, when they go away. And so now, with this additional information, we can take our network, right? And what we'll do with it is, first we'll extract just the list of edges from it, right? That's what we're doing in this line where we're creating a second network, net2. We're plotting it a little bit just to see what it looks like, and then we'll fake some longitudinal data, right? So the longitudinal data in the StatNet universe, instead of start and end for each edge and for each node, they've decided that the words that the parameter names that they want to use are onset and terminus, because it sounds more sophisticated, I guess. And so that's what they're called, but it's the same kind of idea. So what we're doing here is just faking some dynamics in our Zachary club data. We're saying every node in the network is going to start at time point 0 and end at time point 100. And then every edge in the network is going to show up one by one, right? The first edge is going to show up at time point 1 and be there until 100. The second is showing up at time point 2 and be there until 100, and so on and so forth, right? And so there we can, next thing we can use is this pretty fancy library called NDTV for visualizing dynamic networks. And it will take our initial network the way we already had it, and then it will take those dynamic timestamps, right? We'll feed it the list of the data frame of times for the edges and for the nodes in the network, okay? And then the next couple of things that happen on the slide is we take the network, we give it a layout to use, and we say start generating for us slices of time that you will stitch together to make an animation, right? So here we're saying we want an animation that starts at time point 0, ends at time point 100, right? Start 0 and 100. The interval is 4, which means we'll take 4 steps. So 1 to 4 is going to be the first thing that we'll see in the animation. This is the time points, then 5 to whatever 5 plus 4 is, and so on and so forth. And we'll show anything that happens between those time points. And so what that ends up looking like is something like this, right? This is our same initial network. Now it's animated, and now we're kind of looking at it develop over time. And so I have a few other things to show you, but I think we're close to time. So we'll just skip through all of that stuff and just mention the last thing that I want to mention is when we visualize networks, one of the first things that we kind of have to think about is how to place them on a screen, right? So where does each node of the network live on our screens? And there are a number of different ways to calculate that and make that decision. And iGraph offers a lot of those layouts, right? We can place them all on a circle. We can use one of those force-directed spring-embedded algorithms that think of the nodes as a physical system and kind of adjust them on the screen so that they're pulled together by the edges but pushed apart by the nodes becoming too close to each other. That makes for a pretty well-spaced layout. In essence, a layout is just a list of coordinates, of x and y coordinates for each node in your network. You're getting a position on x and y where you want to place it. And so you can make your own in any way you want. And so I think this is where I'll stop, and the rest is in the slides. Thanks.